Okay. Good morning, everyone. My name is Huang from AMD Linux GPU platform team, and works for AMD GPU and the kernel related software support and kernel DRM graphics and GPU virtual memory TTM and AMD ROCm kernel driver and also the whole ROCm compute stack for many years. And I'm very happy to be here to join the Zen Summit again and continue talking about the GPU Para-Virtualization. Sorry. And in last year, we kicked off the passthrough GPU and with QEMU and also virtualized GPU with Virgl and Venus on Zen. And this is the first prototype and to complete the OpenGL and the Vulkan 3D libraries. And this year, I would like to introduce a new way to use the virtual native context instead of legacy, the Virgl and Venus, and also kick off a prototype with the AMD ROCm compute support on Zen. And it is the machine learning applications and for all the AMD GPU hardwares. So any questions and comments, please feel free to interrupt me and during the presentation. All right, these are our team members, and we are working for these solutions. We are from different countries in the world and work closely with Stanfano's team and to deliver these solutions. Daniel and Jiqian are working on the kernel QEMU and Zen, and Pierrick and Julia are working on the Mesa and Virgl render during these two components to implement OpenGL and Vulkan 3D libraries. And Honglei is working on the AMD Compute ROCm stack, including the HSA runtime, Song, Virgl render, and the QEMU. And Liu and Boyuan are mainly working on the Mesa multimedia video. And because the AMD GPU also including the video codec accelerators. And this year, I'm very happy to have a new one, Penny and Lingshan, to join us together to improving this solution. And Penny is the Zen developer for many years, and Lingshan is the virtual voting member and has a rich experience on the virtual spec, and also is one of the virtual kernel maintainers. And recorded last year, and we introduce and kick off the GPU virtualization design on Zen and enable implement the traditional 3D libraries and multiple hardware accelerations based on the Virgl and Venus. And it is also implement multiple video codec and JPEG and VP9 and so on. And this is the first time we try to enable the Vulkan 3D. And at the same time, we also try to submit the GPU passthrough on the PVH domU with QEMU. This is the first time we try to deliver the feature based on the PVH Zen. And then we also bring this solution into the Xorg Developer Conference at October of last year. Xorg Foundation, it is the community that focuses on the Linux open source graphics, and open source graphics, is the AMD official Linux driver delivery for GPU as well. At the same time, and this community is also very happy to see the graphics solution can be supported on Zen, and since the Virgl and the Venus performance, the overhead is very high, we probably try to use another solutions to switch to the open virtual native context. All right, this is the update for this year. Today, I would like to introduce the virtual native context solutions for 3D graphics, both on the OpenGL, Vulkan, and the multimedia hardware accelerations. And also, we'll kick off a new prototype to support AMD ROCm native context solution as well. And for the first step, we are supporting the OpenCL 2.0 with virtual GPU because OpenCL is implemented over the AMD ROCm. It is very complex work because we cannot leverage the graphics API for compute side. We need to totally implement the whole compute stack, the sound APIs by ourselves. And as you know, PCIe passthrough on PVH-guest domU is also in progress for the code review, and we are trying to finish in this year. And we also plan to support the virtual GPU on the PVH-guest domU plus the PVH dom0. Probably is a PVH anywhere in our GPU side right now. And this is a new change from the Lexi HVM guest to PVH guest. And because our target is support the virtual GPU with the Zen Hyper Launch. That's to optimize the booting time of the system. Okay, we separate two sections for the GPU virtualization. The first one, we are talking about the graphics virtualization. All right, please look at this picture. The blob memory, we would like to provide the host memory directly accessed in the guest instead of using the command transfer to write the memory data. And so the guest kernel will expose a MMIO bar and in the PCIe config space for the blob memory. Guest method can use allocate a buffer to allocate a buffer in the guest MMIO bar. Then the host QEMU can create and map a relative the GPU virtual GPU resource to indicate the guest buffer. Then QEMU can get the host virtual address in the virtual render with mmap, the system core, and we expose the AMDGPU DMA bar. However, the host virtual address is not enough for it's not enough for the Zen hypervisor. Zen has to convert the host virtual address to the host physical address with the Zen hypercore and map it to the guest physical frame number with the hypercores. And it is because the Zen is a different hypervisor in the QEMU, the different hypervisor with KVM. The domU physical address is not the real physical address. The real physical address is actually translated by the the PVH domU with the AMD nested page tables. So this is the major work on Zen. And Xenia is right now we are using the painting buffer solutions for the moment, and Xenia is working on a dynamic mapping feature to totally resolve the compute the pinning buffer, because if we use the pinning buffer, the buffer cannot be moved and evict anymore. And now, let's take a look at the following the virtual GPU on Zen. We have multiple GPU virtualizations and solutions on the AMD platforms. In previous, SRIOV is always be used for the data center GPUs, which requires to the hardware and firmware support to separate one GPU to multiple virtual functions. And only few server GPU can support this because they have a hardware limitation. But virtual GPU's way can support the hardware acceleration in a software way. That means we don't have any GPU limitation. We can support all the AMD GPUs. And it is use QEMU to attach the virtual GPU PCIe virtual device to roll the virtual kernel driver. The virtual GPU device is emulated at the virtual bus. Then the user space can implement OpenGL and Vulkan. And right now it's Virgl and Venus for the virtual GPU. And any GPU operations can be rapid by the virtual GPU command to issue to the host QEMU. Then the QEMU will use the GPU virtual render command to separate the different command from the video memory and the system memories. And these solutions we are in progress for the upstream, and these are the links for the upstream work, and it is from the Virgl, Venus, and the QEMU. Yeah, this is the solutions in the last year. Right now, in this year, the traditional Virgl and the Venus is not certifies the performance requirement. So because it has high overhead on the host method. So we are working on developing the virtual I/O native context with AMD GPU on them at this moment. This is the faster way. And this design is initiated by the Rob Clark at the last XDC from the Chromebook system. And then they are used for the native context method to forward the native DRM APIs and from the DRM to the host and to the guest side. And with this approach, we won't need the method. We won't need method in the host domU anymore. So let's can reduce the stack of the method core in the host side. Then our graphics side can do in the similar with the host graphics stack. So we separate the guest method driver in the host or in the guest, and the kernel still running in the host side. So the host method can continue support the 3D application in host, and the guest method can support the 3D application in the guest. So the performance is very, very close with this approach. Then this is the benchmark comparison. We can see the native context way is more than the 80 and the 90% named the bare metal. It's much faster than the Virgl we introduced in the last year. This is the OpenGL comparison with the bare metal. Let's see the Vulkan. Yeah, this is the Vulkan comparison between the bare metal. We can see we over some case we over the 80%, and still have some case need to improvement. In this case, this is the heaviest. The benchmark is Dota 2 and the TERPS and Mad Max. Often also the graphics bench. It is the high bandwidth of the 3D gaming. All right. Let's move to the the GPU is not only for the graphics area. The more important user scenario for GPU is actually the compute support in AI and the machine learning world. And in the automotive market, we also need auto driving, something like that. So the compute virtualization is also very important here. And this is the original design to support OpenCL. And on the guest, and we named it the virtualized OpenCL. The short name is VirCL. This design and OpenCL and the Vulkan stack is there running in the host. then the host virtual render will forward the OpenCL API from the host to guest side. Then the guest can use the OpenCL from end to run the OpenCL applications. Then the guest can run in the OpenCL applications. And they also need to leverage the blob memories. And we need to add the render in Virgl to talk with the OpenCL in the guest directly. This way is similar with the Venus in the 3D. They have a very high bandwidth overhead doing the host OpenGL driver. We have two OpenGL driver running between the host and the guest. So in this year, we use the native context solutions for ROCm as well. Then we use API forward the libsync instead of OpenCL API. Then the sync, we will add the libsync render in the virtual render at host side. Then forward the sync API into the guest ROCm runtime. Then we can go with the OpenCL driver across the ROCm runtime to use the virtualized GPU backend to access the sync API in the host side directly. Then we can know compute running in the host DOM0. And it's very, very close with the host Vulkan as well. So use this way, it's much faster than the original, the Virgl design. So we already kick off the virtual in the graphics free desktop foundation for this approach. And let's see the comparison. Yeah, it is the Virgl and the CL native context design comparison. So you can see we already reduced the work of the here. So only forward original, we forward OpenCL context to the guest side. But in the new way, we switched forward the sync API from the host to guest side. It is reduced the overhead between in the host ROCm runtime and OpenCL driver anymore. So this design can achieve the much more performance here. And regarding to the ROCm native context suite, we have two major features for this solution. The first one is a user pointer. And what is a user pointer? The user pointer is defined for OpenCL flag. We have we would like to allocate a buffer by the malloc, which is a standard call of Linux system. But we would like this buffer to be accessed by the GPU as well. So we have to map the GPU page tables into this buffer. So we always call the virtual address of this buffer is a user pointer. And another is a shared memory, a shared virtual address memory. And we always name it the SVM. This feature is the OpenCL developers would like to use a unified virtual address for the GPU and CPU. It is requested CPU and GPU can share the same address space. And only one pointer can be simplified up level, the OpenCL application design and implementation. This is the ROCm compute requirement. And this is the OpenCL, the ROCm native context user point design. The guest kernel will pin the user space page, while the guest application can allocate virtual memory. And this way is get the guest virtual memories PFNs and register into the MMU notifier. And the hypervisor core where core is the Zen foreigner memory ops and to allocate once the buffer is executing the query behavior in the MMU notifier, then we will use this hypercode to allocate the buffer. And the thunk will register and map the VA with AMD GPU VM functions to generate the corresponding page tables. And then in another side, the similar way with the destroy, we will call the foreign IMAP to free the domU mapped memory as well. All right, this is the design of the shared memory virtual address. We call it SVM and reserve a piece of shared CPU and GPU virtual address in the guest domU and target to make sure the CPU VA be equal with the GPU VA. At the same time, we reserve a piece of mirror GPU virtual address in the host domU, which the start and the sides are exactly the same with the guest side. All the SVM buffers can allocate it in this range at the guest. Once we get the VA range in the guest, it will reserve the same offset in the host domU. The GPU VA equal with the CPU VA, the GPU VA2, and then we map and pin the GPU VA and page tables into the GPU VA2, and the K map to have the CPU VA as well. Then develop the mapping function in them to map the CPU VA domU get map into the guest CPU VA domU. The design, but this design have no issue. We cannot use it for the user pointer right now, and because the guest mylog cannot be assigned a specific VA in the reserve range. So this is also the problem. We need to get resolved in the future. I would like to submit a design section to discuss about this problem, and maybe we can figure out a better way to support the shared virtual memory requirement for the GPU side in Zen. And please look at this picture. This is the data, the performance data comparison of the Virgl and the OpenCL native context. We can see OpenCL native context for compute is close, very, very close with the bare metal and the domU. And it's almost a double conformance of its Virgl. So this is the new way we try to support the better GPU compute virtualizations on domU as well. Yeah. And right now we the next step we were not only to enable the OpenCL. We would like to support the OpenCL and also support heap on the whole AMD ROCm. Once we have the ROCm stack, we can support all the AI and the machine learning application with on Zen. So in the next step, the next step, we are working on the upstream for the whole solutions, and we need to do the full graphics benchmark verifications based on our existing solution. And we also need to provide the formal solutions to completely resolve the direct mapping during the virtual MMIO bar for QEMU and on Zen at blob memory, as mentioned before. And Zenia is working on these solutions as well. And at last, we will continue to implement it, the whole AMD ROCm stack. We will support heap in the ROCm stack. Then we can support the leading AI framework over the ROCm virtualization on Zen, like the MI series, the data center. And we will plan to support TensorFlow and PyTorch and other AI applications. Okay, and this year we already added the new hardware to testing, and the one is our latest Ryzen 8000 series APU. It is ongoing. Traditional, we already support the embedded V2000 series and also the discrete GPUs. And we already talked and our solutions between the last year Zen Summit and also the XORG Developer Conference. All right, at last, I would like to share a demo video to all of you. Yeah, let me. Yeah, it's here. Yeah, yeah. You see, there is two machines running together. This machine, they are running the native context way. This is a new design for the virtual GPU, and this is the next way I demo in the last summit, Zen Summit last year. This is the Venus support for virtual GPU. Then we can start the Steam game with the heavy 3D gaming benchmark. This is Mad Max from Steam game. Then we can play the video directly. Then please notify the FPS of the 3D FPS between compare with the native context. If you see the native context way is average, the FPS is higher than the next way we provided in the last year. Yeah, we can find a better picture to compare with the sorry. Yeah, find the picture to compare with the detail. It's 1 minute. Yeah, if you see, we were notified the left FPS will be always higher than the right one. Once we have a better picture, we can see the details, the text in the top screen. Oh, right. Please see here. It's more clear. The right one is we are running the virtual Venus. It is all designed for Vulkan, for virtual GPU. The Venus is running the Zen guest, and the backend is AMD Radeon graphics. If we switch the native context, we will see the whole. There is no Venus anymore, and virtual stuff. We can run the AMD GPU Vulkan driver directly in the Zen guest right now. So we will use the same way to support all the AMD graphics and compute side. Yeah, if we notify the FPS, we will see the right PS, the left PS is much higher than this one. At least the 10 or 10 to 20%. Yeah. Okay, that's all for my talk. And any questions? Let's watch the video and feel free to let me know if you have any question. Yeah, Daddy.
What is the security situation of this, and who's going to be providing security support when a vulnerability gets discovered?
Yeah, I know it is a very good question. So this is the new development for us in the native context. We still need to consider the security, the functionality in the next step. So far, we only focus on the graphics implementation and not take care much more in the security side for the gas VM. But it's definitely our next step for this.
So is the goal to make this useful for trusted guests?
Yeah. Yes, it's our goal. And because we are, I know you have some security concerns related with this problem, and please feel free to let me know. You can write down, we can mail, and we can discuss in the design sections, and I can talk with our internal AMD's hardware and developers and for address your concern. Oh, all right. Any other questions? Yeah.
It seems like the right one is smoother, although the left one is faster. So the left one is little slow.
Yeah, because we are used manually to kick the application, but you can notice the FPS of the left side. We will say the native context FPS is always higher. The average always higher than the right one. This is only one of the Steam gaming, because if if we do the GPU virtualizations, we definitely not only use the traditional GL mark and something else. We definitely use the heavy 3D benchmark, even the gaming and the heavy the compute stack for the testing to prove our quality of the GPU. Oh, Venus, the major difference, Venus, they can support not only one GPU. Maybe the ARM Mali, maybe the other GPU, they can support open source graphics. They can support Venus as well. But the Venus didn't support on them before. We bring the feature of blob memory to support Venus in the last year. And this year, we will try to enhance the solutions to support a fast way to address the concern of the Venus. So we separate the AMD GPU driver with a new way with native context to address the better performance. But in native context way, we only can use AMD GPU because we separate the GPU driver, the kernel and the user space from in the host and the guest side. Daddy?
You actually can use other GPUs provided that you have sufficient, provided that Virgl render and Venus on both sides have support. This is already shipping for Qualcomm GPUs in Chromebooks.
Yeah, right. Actually, but the Qualcomm GPU they developed it based on the cross VM. You know, the product is the Chromebook, but in this side we bring it into the QEMU. You know, the Zen support QEMU, and we combine the Zen and the QEMU to support this approach. That's different device model.
Okay.
Yeah. Of course, once we have a chance, we will try the cross VM to enable the AMD GPU as well. All right. Any other questions? Okay. No. Thank you.